All right, here we go. So again, if you have trouble getting onto Lumen Learning, please let me know, okay? Please. Sound issues. Try logging out and logging back in. I heard that helps. So I know sometimes changing your browser can help also. That's what I've heard. All right. Okay, so I want to keep going with chapter P. Okay. All right. I think I actually emailed these. Yeah, okay. Anyway, so let me get started. All right. Okay, so if I remember correctly, I think we were up to here, and I just presented what the set of integers is. Okay, everyone can see it. And I presented what the set of integers, what that set is. Basically, again, you take the positive integers, you know, the natural numbers, right? You throw in 0, and you throw in the negatives as well. I mean, -0 is just 0, so -0 is already in there, so to say. Since there are infinitely many integers, that is, there are infinitely many positive and negative, that's why we have this ... notation, right? So before -3, so to say, we have -4, -5, and so on. After 3, we have 4, we have 5, we have 6, and so on. You know, it's almost like the ... notation is saying, and so on and so forth. I know it's a little weird to have it out in front here. I actually rewrote the set this way. You know, we have 0, we have 1, then we have -1, we have 2, -2, we have 3, -3. But again, you can see the pattern, hopefully. You know, so next would be 4, then -4, then 5, then -5, and so on and so forth. So that's a very important set. I thought someone asked the question. My mistake. So that's a very important set, the set of integers. From that set, we can actually get the set of rational numbers, which is the set denoted by this funny looking Q. And it's all fractions of integers. In other words, all the elements in this set are fractions that look like this, P over Q, where P is an integer, Q is a non-zero integer. That's what I'm trying to say here. And such a fraction is actually called a rational number. And you could actually consider rational numbers, these fractions, in decimal form, but we don't have to. That is, I guess I shouldn't say we don't have to, but for time consideration, I'm not doing that. But again, that's what the rational numbers are. They're just fractions of integers. You know, you have the numerator, the number on top, is any integer. The denominator is any non-zero integer. Okay, and these are rational numbers. Now, there are many numbers out there that are not rational numbers. In other words, you cannot write them in this form. Such numbers are called irrational numbers. And there are many irrational numbers. If you remember, I didn't go through it, but if you remember from, I guess, previous math classes, maybe even in high school, they have this formula for the area of a circle, right? Pi times the radius squared. And the circumference is also pi times the diameter, or 2 times pi times the radius. But anyway, the number that pi represents, it's about 3.14, but the number itself is actually irrational, the number that pi represents. There's also a very important number that E represents. It's about 2.718. I mean, why that number is important, that's a little bit beyond the scope of the class. That number turns out to be irrational. We'll see square roots later, but if you take the square root of a number like 2, the square root of 3, those turn out to be irrational numbers. In other words, they're not in this set. You cannot write those numbers as one integer over a non-zero one. I mean, y takes a little bit of work, but what am I getting at here? There are rational and irrational numbers. And then we have the set of real numbers. That's what this R is. And this is the set of all numbers that are rational numbers or irrational numbers. That's what the real numbers are. And really, for the most part in this course, these are going to be the numbers we're going to be working with. Someone had a question? Did someone have a question?
Hi, I'm sorry to interrupt, but I can't really hear you. You're cutting out a lot. I don't know if
Really?
anybody else is having this issue.
Did you try logging out and then logging back in? You could try that. I mean, that's all I can say, really, I guess. Or you can also maybe try a different browser. Oh, she logged off. Okay. All right. Okay, let me just keep going, I guess. So that's the real numbers, okay? Okay. Again, I am recording the lectures, so you can always re-watch them if you want later on, everyone. I will post them to YouTube today. So that's the real numbers. The set of complex numbers, that the book mentions, but really for time consideration, I really don't want to get into them too much, but I just want to mention what they are. The complex numbers are numbers of the form a plus I times b, where a and b are real numbers. So a and b come from this set, but I is the square root of -1. I know normally when you think of square roots, you might think, wait, we can't take the square root of that number. We're basically calling that I, though, almost like imaginary. Or if you want, you can think of I as the number whose square is -1. We're almost like pretending that there is such a number, and then we're seeing what implications that has. That's the set of complex numbers. But for now, let me just skip over that. I just mentioned what they are. I really generally don't have time to go into that. So let's move on. Anyone? Hope she gets back in. Okay. All right. So again, let me keep going now. Okay, so we know that we can multiply numbers together. Okay. Again, I'm also treating this, I think I said this last time, P1, which we're in, I'm treating that kind of as review. So I am going a little bit quicker than I normally would. Just letting you know. Now, with multiplication, right, we have this idea of, of exponents. And namely, for any real number a and any positive integer n, or if you want natural number n for us, we define a to the n to be a times itself n times. In other words, you have n copies of a and you multiply them all together. You multiply them all together. And really, by definition, a to the 1 is a. So this is really a definition for us. And this is really terminology, and this is what people say terminology. This is what we call the nth power of a, and this is a to the n, or a to the nth power. The a is called the base, the n is the exponent. And I threw in some examples here. 4 we know is 2 times 2. With this new notation, this exponents, we have 2 squared. 81 is 3 times 3 times 3 times 3, which is the same as 3 to the 4th. So 3 is the base, 4 is the exponent, right? We have 4 copies of 3, and we're multiplying them together. That's what we're doing here. Okay. Now, you do have to be careful when it comes to exponents, though. You have to be very careful, especially when the base is negative. Because let's consider this. If you have minus 3 squared, right? Well, with a as minus 3, right? Sorry, I went too fast. From this, minus 3 squared, that's just minus 3 times itself. So we have minus 3 times minus 3, which is 9. By SAP, I think they call it SAP and Sun rules, signs alike, positive. The answer is positive. Signs unlike, the answer is negative. Here, however, if we have minus 3 squared, right, this is actually minus 3 times 3, which is minus 9. Well, these are definitely not the same. So in other words, these are not the same. What am I getting at here? When the base is a negative number, you have to use your parentheses carefully. We have to be careful. I mean, if the minus was not here, then it wouldn't be an issue. But because of these minus signs, you have to be careful, is what I'm saying. All right. So we have that.